Um, Now we'll get into the extended Kalman filter, which is something that kind of looks like a Kalman filter. We use the Kalman filter framework to try to address nonlinear systems. The Kalman filter was for a linear system, and it was really optimal in the case of time invariant linear differential equations. But okay, now we're going to start addressing the nonlinearities. We'll start out with a discrete time situation where here is the system model. This f now is a nonlinear function, and it really means a vector of nonlinear functions. And h would be something similar. It's a vector of nonlinear functions, at least potentially nonlinear. The noise terms are like before for the Kalman filter. Here are white sequences, independent sample to sample, zero mean, okay? So that's the system model. For the rest of this, I'm going to pretty much skip the derivations. And the derivations aren't really derivations from first principles to optimize something. They're just a series of approximations, all using linearization. So you're going to see lots of matrices full of first partial derivatives. It gets kind of ugly. If you're interested in this part, go to my website, my web page, or consult textbooks of your own, because you're getting into pretty advanced application type stuff. You're an advanced student if you really want to understand this thing thoroughly. I'll go through it and I'll do an example or two to point out how things work and how to analyze things a little. I'm going to go light on the derivations. So I'll say I'm going to skip that. I'm even going to skip this. And I'll get right to the results. The extended Kalman filter when our truth model is discrete. And we have a truth model. I just went through this. Here's our new process equation and measurement equation. Now we have these nonlinearities in it. All the noise terms are like before. Zero mean, known covariances, white sequences. And here's our extended Kalman filter equations. We have propagation to get from one state time step to the next time step. And we have the correction equation, which is how to process it once you're at that new time step and now you get the measurement there, how to process that measurement. So it's that same recursive framework of the Kalman filter, very similar looking equations. But we propagate the state by using this nonlinear function. We just put in our estimate. The hat notation means estimate. So our estimate at the next time step is just the nonlinear function evaluated at our estimate at the previous time step. Covariance propagation equation looks the same, but this phi is a linearized version. It's this matrix of first partials evaluated at your current estimate. Similarly, your correction equations look pretty similar to the Kalman filter equations. I think this is the only thing that looks different. You use the actual nonlinear function here using your previous state estimate. But this capital H here is again an approximation. This is a matrix of first partials. These are things you put in a computer. It has to do a bunch of calculations in each step. Let's see. That was if your truth model was discrete time. What if it's continuous time? Which is going to be probably more usual for us. Then we have to do linearization and discretization at the same time. We have to do both of them. So here's our new state equation, our process equation. It's a derivative, it's the time derivative, the differential equation, nonlinear. At least this part's nonlinear. I'm going to limit myself to the input noise is still this linear relationship. So I'm in a way oversimplifying things, or at least I did in my course. So here's what it looks like more expanded. Your state is this vector, it's a vector of state variables, and this F is a vector of nonlinear functions. This U sub D is a deterministic, something we know. It's an input that we know. It's not a random process. This U is our good old white noise, unity white noise. I'm going to say when we had linear dynamics, here was our state equation, x dot equals this fx. And here was our way of finding the state transition regions. We used the inverse Laplace transform. Now we've got this f being nonlinear, and it changes over time. So instead of trying to take Laplace transforms every time step, we're going to use this, but we're going to approximate it. If you recall that the exponential term, that matrix exponential, was this infinite sum. We can approximate it by truncating after only so many terms. And I'm going to satisfy ourselves, and I did in Mike when I taught it, to just the first two terms. Some Kalman filter engineers use more terms, especially up to the quadratic term, for better accuracy or a closer approximation. But we go back to this, and instead of taking these inverse Laplace transform differences. Anyway, to do that, both linearize and discretize, I found textbooks on this kind of lacking. It was kind of frustrating. To me, they left too many exercises for the reader. It's kind of like, instead of telling you what time it was, they told you how to build a watch. You could do numerical integration, yada, yada. So I simplified it for my students. I called it the complete guide. How to do an extended Kalman filter. You were given a continuous time system model, and everything's nonlinear. I'm not going to go through what all these formulas mean. I'll show you how they apply in the next video. But what it means is there are many things you'll need to find. This is going to be implemented in a computer. But if you're given this, for one thing, what is your little f? And then what is your big F? You know, because we have propagation equations and correction equations, and we need to find a bunch of terms. What is little h? What is big H? What is our phi matrix? What is our Q matrix? And you know, everything's going to get pretty ugly. Sorry, they're matrices full of first partial derivatives. So I'm going to show you more by example than by showing you all those formulas. In fact, kind of as we go through this, here's all the things we're going to need to find. And then you put them into this recursive algorithm. So I stress to my students how to find all these terms. Given what you start with is some kind of nonlinear continuous time differential equation, etc. So I'll get into this example in another video. Sorry, I skipped over a lot of the extended Kalman filter, especially how to derive it, which is not really deriving. It's a series of approximations. This is advanced stuff. If you do this yourself or want to do this yourself, consult my website or consult textbooks. You're an advanced student. Congratulations.